My name is Stephanie Jarmak. I am a postdoctoral researcher at Southwest Research Institute, and I'll be presenting on modeling efforts by myself and my collaborators to produce a framework that would yield a high-fidelity estimate of the total dust accumulated and lost over the course of the lunar lander mission, and ultimately provide an estimate for the total dust delivered to Gateway. A key component of any future lunar lander mission is to assess the hazard posed by the lunar dust environment and mitigate those risks wherever possible. For the Artemis program in particular, it is critical to have an accurate understanding of the dust risk posed to Gateway as a result of dust accumulated and lost by the lunar lander over the course of various mission phases. These main mission phases include descent and ascent of the lander, where dust is lofted due to rocket exhaust impinging on the lunar surface, resulting in mass erosion, and dust is lost due to spacecraft surface geometry, impulses imparted to the surface of the spacecraft due to thrust changes and pitch angle changes. The burn and docking phases of the mission result in dust loss due to impulses and spacecraft pitch angle changes, and the dust delivered to Gateway would be the amount of dust dislodged from the spacecraft after interfacing with Gateway. A rough order of magnitude estimate of anticipated dust accumulation and losses could be made by scaling the mass flux produced by the lunar module to the anticipated lunar lander thrust. For our test case, the spacecraft would have twice the thrust of the lunar module, resulting in a mass flux of approximately 2 milligrams per centimeter squared within the vicinity of the spacecraft. By applying simple force balance estimates with anticipated thrust forces, lunar regolith adhesive forces, and lunar gravity experienced by regolith particles, a threshold angle for a particle to become dislodged could be estimated, and the total dust accumulated could then be scaled based on spacecraft surface geometry. However, this method produced threshold angles above 86 degrees, meaning nearly all of the dust would adhere to the spacecraft as long as the surfaces were not perpendicular to the lunar surface. To arrive at a more physically realistic result, we modeled the dust interaction with the plume flow field to produce dust distributions and trajectories during the descent and ascent phases. These parameters would then be input as initial conditions to a discrete element method particle simulation software called LIGHTS. The software could then be used to initialize particles with relevant impact velocities, particle sizes, and cohesion, interacting with a subset of the spacecraft surface that would be subjected to various impulses and pitch angle changes. The outcome of the dust particle, either adhering or becoming dislodged, would then be iterated through the relevant conditions during each mission phase and then scaled based on the spacecraft geometry, dust volume, and dynamic information produced by the plume model and anticipated spacecraft maneuvers. The combination of our plume model with the discrete element method model therefore would provide a high fidelity estimate of the anticipated dust accumulation and losses over the course of a lunar lander mission, resulting in an accurate assessment of the dust hazard posed to Gateway. This framework is scalable to any spacecraft geometry, thrust, and trajectory, and is therefore a valuable tool for undertaking the critical task of assessing the dust risks posed by any future lunar lander mission. Future improvements to the model would include implementing electrostatic effects, which may be important for improving anticipated particle trajectories near Gateway, assessing the effect of irregular grain sizes, and increasing the overall granularity of the anticipated particle size distribution, spacecraft surface geometry distribution, and frequency of impulses and pitch angle changes. Thank you for listening to my presentation, and if you have any further questions, please don't hesitate to contact me at my email address, sjarmac@swiri.org. Thank you.